Now, okay, now we look at the circuit. The circuit with 3 battery and 5 resistor. The current flow through this part is 0.6 ampere. So now we want to find the current in current for I1, I2, I3, and I4. Where is the I1? I1, we look at here. So the current stream, the current flow in this direction. Okay, flow in this direction, is it? So that means that this is the 0.6 ampere. That means that the 0.1 also is the 0.6 ampere. 0.6 ampere. Okay, so the current in that pass through the resistor, they are in series, right? In series, this means I4 also is 0.6 ampere. Okay, now this is 2.4 ampere. 2.4 ampere is going in and combined with 0.6. That means 2.4 plus 0.6 will be 1.2. 1.2 will be 3.0 ampere. After that, pass through this way, that means that 3. I3 also is 3 ampere. Okay, so that means that we use the Kirchhoff's first law to analyze the current flow in the circuit. So from here, as a conclusion, we can say that Kirchhoff's first law states that at a junction, that means that sum of the currents entering will be equal to the sum of the current leaving. Kirchhoff's first law is based on the principle of conservation of charge. Okay. Next. Let's observe the slide. We notice that there is a roller coaster which moves to a maximum height. Maximum height, then going down. So this means that at the maximum height, what happened? This means they will have a maximum potential energy, right? When it's going down, the potential energy will convert to the kinetic energy. The loss of the potential energy convert to the kinetic energy. Now, we are going to the Kirchhoff's second law. Okay, Kirchhoff's second law states that if, okay, first the current, we look at here now, the battery positive is out. Okay, this side negative in, positive out. That means that we assume the current flow in this direction. Okay, that means we have E1. E1 is the EMF for the battery 1, EMF for the battery 2, with the internal resistance of R1 for battery 1, internal resistance of R for the battery 2. So let's say we choose the loop. The loop is A, B, C, D. Okay, so once the loop we choose like that, that means that we assume that the loops, the current flow is according to the loops. But if like that, that means that if the direction of the current, okay, will be positive, okay, current Current is positive or negative because the loop's direction equal to the direction of the current, we assume, right? So that means that the direction of the loops equal to the direction of current. So that means that the current is positive. Okay, all of the current is positive. This I is positive. Okay, the current flow in the circuit is positive. How about the EMF1? EMF1, now the loop's direction, is it equal to the direction the current out in? Yes. So that means it will be positive as well. How about this side? So the current, the loop's direction is going down. That means this side the current is out, this side in. So that means that it will be positive as well. Okay. Negative if it's in the, okay, the current or the EMF is in negative direction. That means that if I assume that my loops is in opposite direction, DCBA, that means that the E2 will be negative, E1 will be negative. Current also will be negative. Okay. Now, let's look at the circuit. This circuit, now we assume that the current flow in this direction. Okay, we also assume that this side, you see, this current, okay, flow in which direction? Because the battery should be out in this direction, right? But this one, okay, we change the direction. Okay, this one we need to change the direction. This one, okay, this direction is incorrect. Okay, this direction should be opposite direction. Please correct the arrow for this one, yeah. So now we assume that for the possible loops A, B, C, D, A, B, C, D, A. Okay. Now the current in the direction is positive or negative. I1 follow the direction of the loops. So I1 is positive. I2 also follow the direction of the loops, right? So it is positive. Okay. So now for this one, E1 now, this side positive out, negative in, right? Follow the direction. So E1 is positive. How about E2? Positive out, negative in. So it will be positive as well. Okay. Then we assume that loop C, E, F, D, C. C, E, F, D, C. Okay. Now E3, that means it should be out in this direction, right? But it's in opposite direction with the loop, so it's negative. Okay. E2 out in this direction, where it's opposite direction with the loop, so it will be negative as well. I3 opposite direction with the loop, so it is negative. I2 also negative direction, so it will be negative as well. If the loops A, B, E, F, A, if I assume the loops are that A, B, E, F, A, look at the loops. Okay, so that means that the direction of the current I1 same direction, so I1 is positive. How about I3? I3 is opposite direction, negative. E1 is up, so that means same direction with the loops, so that will be positive. But this one, E3 out, and the loops, the direction out of the current out, and the direction of the loops are opposite, So it will be negative. So these are the rules for the Kirchhoff second law. Okay, part of the second law. Next. Now come to solve the problems. Back to the question just now. Okay. So the total of the EMF. The EMF positive is connected to the negative, right? Total of the EMF is E1 plus E2 because they are in series. Positive are connected to negative, negative connected to positive. So that will be in series. Because just now E1 same direction, so positive. E2 same direction, positive. E1 plus E2. Total IR, total current that pass through the resistor. We have 1, 2, 3, 4 resistor. So this means I times with R1, positive, right? R is the positive direction. I times R1 plus I times R2 plus I times, okay, R2, the small, plus R1. So this means that IR. So we use the Kirchhoff second law. State that total EMF equal to the total potential difference. Then we solve it. E1 plus E2 will be equal to I R1 plus I R1 capital R1 plus I R2 small r plus with I capital R2. This is the Kirchhoff second law we apply to solve the problem. As a conclusion, we can say that the Kirchhoff second law states that for a closed loop, our algebraic sum of the EMF, that means that the total, the sum of the EMF will be equal to the sum of the product of the current and the resistance. This means that sum of the EMF, total EMF equal to the sum of the potential difference. Total, this means that total EMF equal to the total EMF. Total EMF equal to the total potential difference, equal to the total potential. Kirchhoff's second law is based on the principle of conservation of energy. Kirchhoff's first law is the principle of conservation of charge. Second law is the principle of conservation of energy. And the current of the EMF, okay, the current, the EMF is considered positive if it is in the direction of the loop, same direction with the loops, and negative if in the opposite direction. If the direction of the current or EMF is opposite direction to the direction of loops, so that means it will be negative. Finally, we apply both of the Kirchhoff law to solve the problems. Now, given that for the second situation, given that E is 2 watt, 12 watt, and 6 watt. Okay, resistor 3 at 10, 2, and 4. Use the first law of the, okay, at the point C. We can choose point C or you choose point D. Okay, if choose point C, total in, how much in? I1 is in, okay, into the junction, and then this will be I2. I1 plus I2 will be equal to I. I1 plus I2 equal to I. All right. Then use the second law. I choose the loops for A. Which loops I choose? Okay, B, A, D, C, B. B, A, D, C, B. Now my loops in this direction. Okay, that means same is the current is positive. How about what's that? The EMF positive, EMF positive. So this means 2 plus 12 is the total EMF. Okay, total EMF equal to the total IR. So this means 2 plus 12, this means 14, equal to I. I, how much is it? This is I. Okay, I times with, okay, this one is I times with 4. Okay, 1 times I. That is for the first internal resistance, 1 times I plus with the 4 times I plus with 2 times I, okay, plus with I1 times R1, I1 times R1, okay, that is 4, plus with the I1 times, how much? Times 10, okay, I1 times 10, I1 times 4, then the rest we use I. Then we get it 7I1 plus I2 plus 14I1. So this means we simplify 21I1 plus 7I2. Next, still using the same concept, then we solve it. 14 equal to 21I1 plus 7I2. That means let's say we simplify, we get it divided by 7. Okay, that means we get 2 equal to 3I1 plus I2. Okay, then this, okay, that means that we use at the point C. So next, what we can do for next, we just solve one loop only. Yeah. So what happened if we continue again with the second loop again? Now at point C, same thing, but now the second loops we use DCFED. DCFED. Now we notice that the loops is like that. Okay. 12 is positive. 12 watt is positive. 6 watt is in negative direction. This means that 12 minus 6. Okay, because negative 6. So, and how about the I? So R1 and I1 is in positive, right? But this will be I2. I2 is in negative direction. Okay, I1 times with I1, where is it? I1 times with 4 plus with I1 times with 3. Okay, M1 times 10. Not. After that, this one negative minus I2 times 8 minus because negative direction. And this negative again minus 3 I2 minus again 2 I2 minus 2 I2. Okay, no more resistor. So we solve, it will be 6 equal to 14 I1 minus 13 I2. We have by, okay, get back the equation just now. Okay, so solve it. Just now 2 equal to 3 I1 plus I2. 6 is equal to 14 I1 minus 13 I2. Equation 1, equation 2. Okay, don't forget we have the equation just now. I equal to I1 plus I2. Then we solve it. Here we get that I2 is equal to 0.118 ampere. Then I1 is equal to 0.6 ampere. So the I is 0.792. All of the current, we get the value is in positive. Positive means that the I 0.792, this will be 0.792. Positive, right? That means same direction. That means the current is flow in this direction. I assume what I assume is correct. And then I2 positive, I2 is positive. That means the current flow in this direction. Okay, current flow in this direction. Okay, so And I3, I2 we get 0.1. Sorry, I1 is 0. I is 0.792. That means in 0.792 flow in this direction. That means all of the direction we assume are correct. If I get this is negative 0.792, if I is negative 0.792, that means what I assume is flow in this direction, right? But actually it's flow in opposite direction, going down. Okay, so this is how we apply the Kirchhoff first law and the Kirchhoff second law. Summary. To apply Kirchhoff first law, we must use the first law for each junction and use the second law for cross loops. The number of independent equations should be the same as the number of unknown. Okay, so now what I want you all to do, okay, same. Later I will post the exercise to our Telegram group. So ladies and gentlemen, what I want you all to do, you try to solve the question first. After that, you just check the answer. Mostly in exam, so they will ask us to solve the Kirchhoff law question. Okay, so for the question I will post later. Question 1, question 2, sorry, actually this is the question 1, question 2, question 3, question 4, question 5, and question 6. Okay, so please solve all the questions first before you check the answer. Okay, so thank you very much for today's lesson. So before we end this lesson, so any questions, student? Okay, so if no, so I end the lesson, yeah.